So if I have rho of this form, the eigenvalues of rho are just the vector of probabilities. So when I demand that rho is positive semi-definite, what does that say about P1 through PD? What does that condition that rho is positive semi-definite, what does it imply about the P's? Yeah? Right. It implies, so rho positive semi-definite implies, in fact, is equivalent to each Px being greater than or equal to 0. You mentioned another thing, which is that they add up to 1, which is a property of probability distributions. But we need more than the fact that rho is positive semi-definite to give that. We need there's trace 1, exactly. So the trace of rho is just the sum of the diagonal entries. And of course, that should equal 1. And this equation is a two-way street. We could have started with the fact that this is a probability distribution, and then we know that's normalized. So we derive that this is trace of rho is 1, and thereby it's a valid density matrix. We could have gone in the other direction as well. We could have said, suppose rho is a matrix of this form, and I claim that the entries correspond to a valid probability distribution, and that's because the trace of rho is 1, so I know that these entries add up to 1. And because of this previous fact, I knew that they were non-negative. So this is how probability distributions can embed into density matrices. Now, one important aside is that this is for diagonal density matrices rho, but the eigenvalues of rho are always probability distributions. So why is that? Essentially, it's the same argument. If a matrix, since rho is positive semi-definite, its eigenvalues are always non-negative. So that's one of the conditions to be a probability distribution. You have to be the entries are non-negative. They also always add up to 1. And this is because the trace is independent of basis. So if the eigenvalues of rho are lambda 1 through lambda d, then trace rho is the sum of these eigenvalues. One way of seeing this is that we can always choose to take the trace in the eigenbasis of rho. So this was a fact about diagonal rho, but if we diagonalize it, then in the right basis, everything looks diagonal. Then for any density matrix, the trace is equal to the sum of the eigenvalues. And so the eigenvalues are always non-negative and sum to 1. So they always form a probability distribution. And so in a sense, that shouldn't be surprising. All we had to do in order to get here is choose some fixed orthonormal basis and call that the canonical basis. But we always could have chosen the eigenbasis of rho and called it classical in that basis. All we did really was, I said fix a basis. You could also say get rid of superposition. But superposition is sort of a mathematical construct, right? States are just some vectors. What we call superposition means we're taking linear combinations of some chosen set of vectors. And so if we just choose our vectors in the first place to be the eigenbasis of rho, then at least for that state, we've defined away superposition. Of course, once you have multiple states or time evolution, you can't ignore superposition forever. But if you're looking at any one state, you can always choose to look at it in its eigenbasis. And on that basis, it looks essentially classical. Even a pure state, if you look at it in the right basis, just looks like a deterministic probability distribution. There's some basis of perfectly distinguishable states, and we have one of them. It's sort of not very interesting, but you can look at it in that way.